Okay.
Okay, can you hear me?
Yes.
Okay. So I
Okay,
can share
hands-free
screen.
digital musical interface for quadriplegic musicians, prototypes, and design perspectives.
Okay, can you also see the screen?
Yes, perfect.
Okay, perfect. Ok. Okay, I'm Nicola Davanzo from Laboratorio di Informatica Musicale, University of Milan, and I think the best way I can contribute is just to show my project, which is about hands-free digital musical interfaces for quadriplegic musicians. I will show you some of my prototypes and some design perspectives that I have. And since my PhD, I focused on musical interaction for quadriplegic users, mostly because, of course, musical instruments are typically played through hands or feet, so quadriplegic users are typically excluded, completely excluded from the world of music performance. I wanted to make them able to play, let me say, a classically defined musical instrument. What I mean by classically defined, in recent literature, I found that also stuff like sequencers, turntables, live coding are called musical instruments or musical interfaces. But I'd like to, I wanted to make quadriplegic people be able to play something that resemble more, I don't know, a guitar or a piano, a skill-based instrument where an action results in an immediate tangible response. I come from an engineering background, so I try to tackle the problem from a human-computer interaction approach. And the first thing that I did it was to try to see all the interaction channels available for a quadriplegic musician. And I divided them into 4 categories. Those belong into the eyes area, mouth area, head and neck area, and mind area. And I made this list. You can see that the 4 groups, and for each group we have a channel, a specific channel. A list of specific channels. For example, under the category eyes, we have gaze pointing, but also blinking. And within the mouth category, we have whistling, we have breath, head, we have head movements. And each of these channels have various degrees of freedom, which I call parameters. And these are basically mostly, not every of them are independent each other. For example, under gaze pointing, we have 2D coordinates of the gaze pointing. Under whistling, we have whistling pitch and intensity. Under head movements, we have all the degrees of freedom in which the head can rotate and move. And then I tried to see if there were sensors able to pick movements from these channels available in the mass market. So, for example, eye trackers, motion trackers, and sip and puff sensors, etc. But I also tried to see if I could make and build specific sensors. For example, this is a very simple head tracker built using Arduino and a chip, the gyroscope chip. I frame my project outputs in these categories, of course, theory and design concepts, but also digital musical interfaces prototypes and design and customization facilities. For me, digital musical interfaces are just pre-built packages which work and implement a particular interaction solution, but of course they are customizable. My general leitmotiv is to try to stick with open source, affordable, simple, and fast and customizable stuff. Let's speak about my digital musical interfaces prototypes. The first of that I made is called Netitar. It's a monodic instrument. It just plays 1 note per time. It's controlled through gaze pointing for note selection and breath to control notes intensity and attack and dynamics. For gaze pointing, I have this guy here, which is an eye tracker. And for breath intensity, I built a custom breath sensor. This is Netitar's layout. It's really peculiar. Every one of these dots, color dots, it's a note. And you just have to gaze them to select them. And the layout is specifically designed to solve gaze interaction problems and to make gaze interaction really easy. And the second one is called Netichords. Is an extension of Netitor which can be used to play chords. Again, it's controlled through gaze pointing, through eye tracking, and head rotation in this case on the yaw axis, like saying no, like in this this way, is used to control chord strumming. Each one of these is a chord, and again, the layout is designed to minimize eye movement and solve specific eye interaction, gaze interaction problems. Then I have this guy, which is probably a crazy idea that I had, which is called Resin. It's again a monodic instrument, and it's controlled to internal resonances in the vocal tract to perform note selections, and head rotation along the again the yaw axis to perform intensity and attack control. What I mean by this internal resonance in the vocal tract, I mean that I put a sine carpet, I mean a sum of various sine waves, which are played by a speaker and conveyed to the mouth of the performer using a tube. So basically, in the mouth, you have all these sine waves and summed together. And by varying the shape of your mouth, so varying the shape of your vocal tract, you make one of these sine waves resonate. And this information is picked up by a microphone, which is again inside the mouth, and transform into a MIDI pitch. So basically, this is a MIDI instrument. And again, we have head rotation, which is used for intensity control. And in this case, you simply have to move your head like again on the yaw axis, like a violin bow or something like. And then we have DJI, which is an interface for DJing controlled through gaze made by one of our students, and Kirol, which is another gaze-based interface controlled through eye tracking again. Of course, I don't have the time in 10 minutes to show you all of these instruments, but they are all free open source software. So, and of course, I will provide a QR and a link to my website where you can find demo videos, more informations, and download links. So now let's speak about my most recent project, which is about customization facilities, which is called NITH. NITH is a framework, a modular framework, open source, to try to enable building and prototyping new instruments more easy, and like streamlining the creation of customized interaction methods for specific users to achieve customization in a few words. The contents of this framework are mainly a collection of sensors and of custom-built sensors, and some libraries, which are called Night Library and Nitmice. The sensor are these guys there, which are really simple and custom-built and do-it-yourself sensors. Of course, for machine interaction for quadriplegics, and they are built using open source hardware plus do-it-yourself materials. As you can see, the materials are really simple. This is like I don't know how to call it, an ice cream stick with a sensor, and this is a teeth pressure sensor. This is a breath sensor using Arduino Uno and some like tubes that you can find on DIY stores, and this is a net tracker. And I tried to make them as affordable as possible, low cost as possible, and easy to assemble with easy instructables. And they all share a common communication protocol, so which is this guy here. Sorry for the technicalities. basically having a common communication protocol make them interchangeable. You can just switch the sensor, and if you have a software which is compatible with one of the sensors, it just works. And then I have NIT wrappers, which is again a collection this time of software middlewares to turn commercial hardware into a NIT compatible sensor. Simplifying with an example, NIT webcam wrapper, for example, is a software to turn your laptop webcam into a detector for head rotation, eye aperture and blinking, and mouth aperture. And the output, again, is through this simple communication protocol here. I provide also this interface, this application for sensor testing with a lot of gauges to see the data and stuff, and to see, for example, if you build a sensor in the correct way. And my idea is to try to cover all of the direction channels available for quadriplegic people, both with sensors, custom-built sensors, or commercial sensors. And libraries, of course, are made to written in C# and made for communication with the sensors, providing receivers, modules, filtering capabilities, preprocessing and stuff. And but I also have a library specific for accessible digital musical instrument development, providing utilities for musical interface development, like MIDI interfacing, audio, and other things. My vision, I want this stuff to enable easy development of new interfaces for people with quadriplegia, and enable swift customization and tailoring for specific users. This is because in my, I have to say, limited experience with people with physical disabilities, I saw that they all have very different abilities. And it's really difficult to make a one-size-fits-all solution. Just to exemplify why I think so, I provide you with an example, not music related, but quite expressive example. I met one person that I called Person X for privacy, which is quadriplegic due to spinal cord injury, and he couldn't use an eye tracker because he could see only through one eye or the other selectively. He could select the eye through which he could see. But the problem is that the eye tracker is really, really not precise with just one eye. So he couldn't use eye tracking for mouse control, and instead he used the voice command with a software called MouseGrid to emulate mouse. The problem with MouseGrid is that, yeah, it works, but it's really, really, really slow. I mean, 6 seconds or 10 seconds just to make a click on the screen. So about this interface, this application in really, I don't know how much it took for me, but some weeks, not more, which is custom made for this this guy, and it uses the webcam wrapper that I show you, and the tracker, the webcam wrapper, to perform clicks, mouse clicks, using your eyes or mouth aperture, and the tracker to control the mouse positioning. And in this case, just to add a detail, you use head roll, this movement here, if you can see me, to select which mouse button to click on. So as promised, there's a QR to my website or a link where you can find all the demo videos and stuff. So thank you for your attention.
Thank you very much, Nicola. And questions from participants? Very, very interesting, your research.
Yes, please.
Yes.
Thank you, Nicola. Thank you very much. You are very prolix. I don't know how to say in English. You made a lot of devices, and it's very interesting.
Maybe too many.
And a technical question. It was a little bit fast. So you say that you implemented in OSC open sound control communication or UDP so that we can communicate with the outside world. That's it.
Yeah, it's not really OSC.
Okay.
It's just it just goes to through UDP or the USB buffer connection. It's not
Okay,
OSC actually, but yeah, it's really simple.
We can translate. Yeah. Okay.
Yeah.
Thank you very much.
Okay, we are perfectly in time. If there is another question, we can accept it.